technical detail.
Yeah, which is actually pretty funny. I like that about the example. Okay, thank you very much. So thanks again for this nice talk. I guess there will also be a chance to talk with you about this in the coffee break after this session. So I'd like to move on to the next speaker, which should be Khushraj Madnani. And you can now.
I'm sorry, it seems that he's still not here. So I will.
He's still not here.
So I will also play his pre-recorded video.
Okay. So we will just have a look at the video. Enjoy. We have. I can still introduce him, although he's not here. So we're listening to a talk now by Khushraj Madnani, who received his PhD in 2009 from the Indian Institute of Technology in Bombay, and is now a postdoc at TU Delft with the Delft Center for Systems and Control. And his talk is on generalizing non-punctuality for time-temporal logic with freeze quantifiers. He will probably also tell this in the talk itself. Enjoy.
Thank you for attending my talk. I am Khushraj Madnani, and I'm going to talk about generalizing non-punctuality for time logics with freeze quantifiers, from non-punctuality to non-adjacency. This is a joint work with Professors Manuel Mazo Jr., S.N. Krishna, and Paritosh Pandya. Temporal logics are intuitive class of formalisms used to specify constraints on ordering of events, using natural modalities like until and since, which can further express modalities like eventually, always, past, next, etc. Classically, these logics cannot specify real-time constraints, like every request from client should be processed within next 5 minutes. Hence, real-time extensions for these logics were proposed and are studied to eliminate this lacuna. Two of the most important problems for these formalisms studied in the literature are how hard it is to check whether any given formula has a model that satisfies it, and how expressive is a given class of formalism. Ideally, we would like to have logics which are highly expressive and for which satisfiability checking is easier. But the above two properties are generally complementary. Time linear temporal logics are real-time extensions of linear temporal logics. Two of the most natural ways to incorporate timing within LTL is by guarding the until and since modalities with timing intervals, giving rise to metric temporal logic, and by extending LTL with freeze variables, resulting in time propositional temporal logic. The formulae of these logics is evaluated over timed words, which are extension of words where every position is associated with a timestamp. We now present the semantics of MTL and TPTL via an example. Any point I in time word row satisfies A until I B if and only if there exists a point J in the future within interval I, and where B holds and A continuously holds between I and J. Since is just the past analog of until. As mentioned before, Tptl can have freeze variables. In this case, X and Y are the freeze variables. As the name suggests, freeze variables can be frozen using these quantifiers. And one can assert timing constraints over them as mentioned in the formula. Now, the first point of any time word row satisfies this formula mentioned here, if and only if X and Y are frozen at the first point, that is X and Y take the value 0, and at the next point A is true, and X is frozen, which means X takes the value tau 2 and Y still remains at 0. And again at the next point A is true and Y is frozen, which means Y takes the value tau 3 and X still remains at tau 2, and eventually there is a point in the future where the marked subformula is evaluated, which means B is true and the time difference between the present point and the last point where X was evaluated, that means tau k minus tau 2, is within 1, 2. Similarly, the time difference between the present point and the last point where Y was frozen is within 0, 1. What do we know about these logics? Satisfiability checking for MTL and one variable fragment of TPTL is undesirable in general. But if you restrict to only if you restrict to use only until modality, then you get a satisfiable, you get a desirable logic, but only over finite time words, albeit with non-elementary complexity. Multiple variable fragment, in fact even two variable fragment of TPTL is undesirable without sense operator 2.
The audio is
But
getting very choppy.
compete
Do
with
you have the
MTL,
same problem?
you don't need
Yeah. My computer, it is always not very noisy, a little noisy.
Yeah, maybe just
Yeah.
stopping the video and starting it again helps. Can you try that, please?
Oh,
TPTL, even one variable fragment of TPTL is strictly more expressive than MTL. It's because every formula
it is
in
better now.
MTL can be trivially written in one TPTL. Moreover, the following formula in one TPTL is not expressible in MTL.
The audio is good now, but we missed some things, right?
There are 2 points within interval I, such that the earlier point satisfies phi, while the latter satisfies psi. To summarize, in terms of expressiveness, one TPTL is the winner. In terms of satisfiability checking, it's a draw. But MTL and its variants are arguably more popular than one TPTL. Why is that so? In our opinion, one of the main reasons is that if we restrict the intervals of MTL to be non-singular or non-punctual, we get a subclass called metric interval temporal logic, which is desirable with X-space complete complexity. In this logic, you can express that an event A, you cannot express that an event A occurs exactly after 5 seconds, but you can still express that A occurs within next 4 to 5 seconds. Unfortunately, no such natural desirable subclass for one TPTL exists. Now, to tackle this situation, we propose a generalization of non-punctuality called non-adjacency for one TPTL reaping identical benefits. We first define what is non-adjacency. Two intervals are adjacent if the supremum of one is equal to infimum of other. Hence, two intervals are non-adjacent if either they have gap in between or they overlap each other. A formula of one TPTL is said to be non-adjacent if and only if, in positive normal form, intervals appearing within the scope of the same Fries quantifier are non-adjacent or are adjacent at 0. Note that as every punctual interval is adjacent to itself, the above condition by default disallows all the punctual intervals except 0, 0. We show that the proposed logic is strictly more expressive than MITL. In spite of that, the satisfiability checking problem for this logic is as easy as that of MITL. The former can be showed by the same counterexample as shown before to compare one TPTL and MTL. Hence, we focus on the more interesting decidability result. Given any NA1 TPTL formulae psi, we check its satisfiability by constructing an equisatisfiable formulae in EMITL 0 infinity, for which satisfiability checking is p-space complete. The construction goes via a series of reduction, which incurs exponential blow. Hence, we have a X-space procedure. We start with a simple NA1 TPTL formulae. The definition of simple formulae is given a little later. Generalizing this result to all of NA1 TPTL is a routine process and can be found in the paper. We introduce two new formalisms or machineries highlighted in the purple box, which was required to realize this reduction. We first start with presenting semantics for EMIT as 0 infinity. EMTL, or Extended Metric Temporal Logic, is an extension of MTL with automata modalities proposed by Wilke. It has two modalities, F and its past analog P. F takes as an input an interval and an automaton over subformulae. In this case, it's alpha and beta. Any point I in time what row satisfies
The audio is choppy again. I don't know whether restarting again, solve the problem again.
And the pattern of satisfaction of the subformulae alpha and beta between I and j, including I and j,
Runking, can you?
given by the above formula. So in this case,
Can you try to restart again?
Okay, okay. The
It helped last time, so maybe restarting helps again.
okay.
it is an extension of MTL with automata modalities proposed by Wilke. It has two modalities, F and its past analog P. F takes as an input an interval and an automaton over subformulae. In this case, it's alpha and beta. Any point I in time word row satisfies the above formulae if there exists a point j in the future within interval I, and the pattern of satisfaction of the subformulae alpha and beta between I and j, including I and j, is given by the above formulae. So in this case, alpha and beta hold alternately between I and j. EMITL 0 infinity is a subclass of EMTL where timing intervals are restricted to have 0u or L infinity, are restricted to be of the form 0u or L infinity. We now define the new logic we introduced called PN-EMTL or NewL-EMTL. The modality of PN-EMTL are extension of that of EMTL with arbitrary arity k. Hence, Fk takes as an input k intervals and k plus 1 automata over subformulae. Any point I in time word row satisfies the above formulae if there exists point I1 to Ik in that order such that I1 is within capital I1 of I, I2 is within capital I2 of I, and so on. Moreover, the behavior beyond Ik is given by Ak plus 1, and the behavior between I and I1 is given by A1, I1 and I2 is given by A2, and so on. The subclass NAPNMTL is derived by restricting the set of intervals appearing within the same modality to be non-adjacent amongst themselves. We now introduce the framework of anchored interval word abstraction. An interval word is a word over a product of finite set of propositions and finite set of timing intervals along with a special symbol called anchor, which holds exactly at one unique point in the word. These words can be seen as abstractions of set of time words. For example, in the given case, it abstracts time words which behave identically with respect to propositions of sigma, and the second point is within -3, 0 with respect to the third point, which is the point corresponding to the anchor point. Fourth is within 0, 3, and the fifth is within 1, 2. And the rest of the points are free of any explicit time constraints. We now define what is a simple formula. A formula is simple if it contains only one outermost freeze quantifier, followed by a quantifier-free formula. Hence, such a formula specifies timing constraints of events appearing in the future and past with respect to the anchor point where the variable x was frozen. Thus, it is very natural to abstract models of these formulae using anchored interval words. We now abstract the set of time words accepted by the formula psi using an LTL formula over interval words. This formula can be reduced to an NFA A. The last two steps forms the crux of the technicality of this paper. We now refine the NFA A using the logic NAP and AMTL, constructing a formula phi which is equivalent to the given formula psi. For refinement, note that while a path in A is unbounded in general and hence have unboundedly many.
So I have to start again now. And 11 minutes. Very sorry for that.
Not your fault. Technical issues. Nice that we have this video and that you found a way to solve this. Thank you.
Thank you.
Given formula psi, for refinement, note that while a path in A is unbounded in general and hence have unboundedly many intervals imposing constraints, a PNE-MTL formulae can only assert timing constraints over boundedly many points. Hence, we propagate interval constraints across positions and normalize the interval worth, bounding the number of constraint points. To bound this occurrence, consider the following example. Note that the restrictions imposed by the first and the last point where 1, 2 occurs implies the same for all the intermediate points. Hence, 1, 2 occurring in these intermediate points are redundant and can be deleted without affecting the corresponding time language. Deleting these redundant entries, we get what we call as normalized words. Finally, note that doing this for all the intervals, we get a bounded number of such interval restricted points, as every interval now occurs at most twice in these normalized words. Hence, given A, we construct A prime, which accepts normalization of all the words accepted by A. This A prime can then be reduced to an equivalent NAP-NMTL formula. We now briefly skim through the last step of the reduction using a simple example. Consider the given formula. By semantics of PN-EMTL, there exists I1 within interval 1, 2 followed by I2 within interval 3, 4 from I such that the behavior between I and I1 is given by A1 and behavior between I1 and I2 is given by A2 and behavior beyond I2 is given by A3. We insert counters at integer timestamps which increments modulo 4. Note that due to non-adjacency, there is we guarantee that there is at least one counter between I and I1 and between I1 and I2. We use these counters to split the check of automaton in two parts, and we assert the partial checking of automaton using EMITL 0 infinity formulae. Finally, we conclude our presentation with a variant of Newelly conjecture. Consider the following property. There are two consecutive points within interval I in the future such that the first one satisfies phi while the next satisfies psi. This property can be trivially written using NA1 Tptl formulae as shown. We conjecture that this is not expressible in Newelly MITL, which is the most expressive logic known yet, making our logic strictly the most expressive fully decidable logic known yet. Finally, as a future work, we plan to explore non-adjacent fragments of other formalisms, to propose on-the-fly procedure for satisfiability checking of NA1 Tptl, and finally proving the variant of Newelly conjecture as proposed in the previous slide. Thank you very much for listening to me.
Yeah, so thank you very much. The speaker is not here, but I think that talk gave some nice intuitions to the rather technical paper. So this was very nice. We cannot ask questions now. That's a pity, but as the technical issues used up all our question time, we are actually pretty happy that we can move to the next talk just in time.